last time I stopped at defining inner product, so it is non-degenerate, positive definite, symmetric bilinear map. In fact, this is true when it is real vector space. So I mean, when V is real vector space, this is true. But if it is complex vector space, V is, this is wrong. I mean, it is inconsistent. Consistent. Why? Because let us check positive definiteness. So positive definiteness tells that if V is in V and V is non-zero, let us assume this, then V dot V is positive. We also know that if V is in V, then I as multiplied to V is also in V. Then, because it is vector in V, we can think of inner product of itself. So we can think of I heart V times I heart V. And because inner product is bilinear, bilinear, then what we have is S multiplied number I square can come out from the inner product. So it is like this. And because I square is 1, so it is minus V dot V. And V dot V is positive, it means this is negative. But positive definiteness tells that for any vector, inner product, use other one, inner product of itself should be positive. But in here, you show that it cannot be positive. So in complex vector space, bilinear and positive definite cannot come together. So you have to give up one thing. And when we define inner product in complex vector space, we give up bilinearity. So we define new almost bilinear, but not exactly bilinear. It is called sesquilinear. And sesqui means just 1.5. So it is almost linear, but not exactly linear. So we define, let us say, this notation. And this is also map, which get two vector and give some number. Let us say k, because it can be complex or a real number. And sesquilinear is that two property. It is linear on right slot. What it means is that if you have, so for all V, U1, U2, of course they are in V, and V times, let us say also A is in field. Okay, let us be general, because sesquilinear can be defined in any case. So any field K, then A heart U1 plus U2 is A times V comma U1 plus V comma U2. And similarly, it is you can say about left slot, but it is not linear. It is anti-linear. So anti-linear on left slot. This is the difference. And anti-linear is that you can do the same for V1, V2, U in V. let's say A heart V1 plus V2 comma U. It is almost linear. So let us say almost linear. So first write linear form and V1 and V2 U. But the difference is that because this anti means that when you pick out the number scalar, you get complex conjugate in the left slot. This is the difference. The sesquilinear is that almost linear, but when you pick out the number, you get complex conjugate. And now, if you define you can say also about symmetric in this sesquilinear form. But the difference is that if you say let's say some simple case, A times U comma V is V comma A times U, then right one is A times V U. Left one is A bar times U comma V. So they cannot be the same. So you cannot define it like this. But if you do some complex conjugate here, it can be happily done like this. So then now complex number come out consistently. So now we can define symmetric. So in the more general way, so we say sesquilinear map is symmetric if U V is V U bar. So sesquilinear map, this one is symmetric if this is true. Again, keep in mind that there is complex conjugate when you change the sign. And for complex vector space, symmetric sesquilinear map has name. Is what you are familiar called Hermitian form. Sorry, I say map, but in fact it was field I noticed that because it goes to just to scalar. So I say this is form more exactly. So symmetric sesquilinear form is Hermitian form. And now you can define general way inner product. So let us say the same. V is, let us say just K vector space. Then we can do the same is inner product. Almost the same. We want non-degenerate. What is symmetric? You keep symmetric, but now non-degenerate symmetric, positive definite, not bilinear, but sesquilinear form. Then this is inner product. Every definition is same. let us check the problem is solved. The problem was that if V is positive, then what happens? IV times IV. This was problematic part. And now, because of sesquilinear, we can go slowly. IV times I times V. And IV, maybe to be consistent with the previous notation, I'll not do anything, just I'll keep S multiplication sign. I heart V. Then this is I times I heart V, comma V, and this is I times minus I times V, comma V, and this is 1 times V, comma V. And when this is assumed, and this says that this is positive. So now, if we define this way, symmetric sesquilinear form, sesquilinear form, it can be positive definite always. So now it becomes consistent. The next thing is that, do we really generalize the definition before? It can be easily checked by that. What happens? V is real vector space. When V is real vector space, A bar is always A because their complex conjugate of a real number is always itself. So it becomes linear, then it becomes, so it is bilinear. Again, symmetric definition, complex conjugate is itself because there is no complex conjugate. So really, this definition reduced to the definition I defined last time. So now we can say that we define some well-defined inner product in complex vector space. Again, in summary, inner product is just non-degenerate, symmetric, positive definite, sesquilinear form.